Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 57. Now in the previous lecture, we were looking at the energy levels of quantum mechanical rigid rotor system, which was helpful for us to understand various aspects about purely rotational spectroscopy and how that is useful in quantities associated with astrochemistry, for example, the rotational temperature, etc. So I had in the last class ended by telling you that the energy difference between any two level is given by this this expression 2b. We had explicitly shown it for j equals 0 to j equals 1, right? Now I'd asked you as a homework to work out delta I between j equals 1 to 2, j equals 2 to 3 and j equals 3 to 4. What did you find the answer to be? Well, irrespective of what j you choose, right? Delta E always. In other words, right? In other words, let's say, if you actually get a real spectrum, that is a plot of your intensity versus frequency, let's say, right? A spectrum is going to have a series of lines. For example, simply, I'm just giving you a simple example. For example, let's say, we have some spectrum like this. It's just a representative spectrum. The gap between any two lines, right, is a measure of the energy, difference. So the gap between any two lines, so all of this, right, this, right, this, and this, right? The gap between any two experimentally obtained lines in a spectrum is given by 2b. Gap between any two lines is given by 2b. In fact, it is exactly equal to 2b, when we consider the rigid rotor model. Are we clear? Now you see, right, on Earth, right, when you get a rotational spectrum of a molecule, which happens to occur in what region of the electromagnetic spectrum? We've seen this before, right? It happens in the microwave region, okay, right? That's also why, purely rotational spectroscopy is also synonymously called as microwave spectroscopy, right? So the gap between any two lines, right, is a measure of any two experimentally obtained lines. So this is experimentally obtained. This can be experimentally obtained. So the gap between any two lines is given by 2b, all right? Now, so therefore, right, now because your b is associated with your moment of inertia, recall the formula for b, right? It is something like h square divided by 8 pi square I, if we want to measure it in terms of energy units, okay, right? So because your b is connected with the moment of inertia, and moment of inertia in turns is connected with not just the reduced mass of the system, but also with the bond length, right? I equals mu r square, correct? So therefore, right, knowledge of b, obtaining b can be obtained by experiments. So knowledge of b actually gives me an idea about the bond lengths of molecules. See, for example, we compile a list of the bond lengths of molecules, right? How do we obtain from it? One very reliable way. Who has seen it, right? Because the molecules are very small. We cannot measure it using a scale or a vernier calipers, etc., right? But one absolutely reliable way to measure the dimensions of molecules, right, is given by microwave spectroscopy. And that is why this is a very powerful technique, not just about detecting molecules in space, but also to find out the dimensions of molecules on Earth. Okay, so now you see the gap between any two lines is given by 2b. But notice that this gap between any two lines is 2b only when the rigid rotor model is going to be holding good. Okay, right? When rigid rotor model holds good, then the gap is exactly equal to 2b. What gap am I talking about? The gap between any two spectral lines obtained in an experiment. Okay. Now, what happens is for transitions from higher j, you can safely say like j greater than 4 approximately. Okay, right? Whenever for transitions happening from j greater than 4, right, that is, we're talking about the higher energy states of the rotational energy level. Okay, right? So when transitions happen from j greater than or 4, right, then the gap is typically less than 2b. All right. Why is that? Well, because the rigid rotor model no longer holds good. Do you understand? Because see, when we are talking about the lower energy states, lower rotational energy states, right? Well, you can safely assume that the energy present, right, is going to be lower too, given the expression, right, is what is it? B times j plus 1. All right. But as higher j's get populated, the energy of the system is going to be more. Consequently, what happens is that there is going to be some vibrational manifestation also. In other words, the molecule is not just going to rotate; it is also going to undergo some vibrations, etc. Okay, right? As a result, therefore, there is going to be a deviation from this gap of exactly 2b. All right. So that is why, right? That is why, especially when we consider rotational states from higher j, right? Rotational transitions starting from higher j values, the gap is less than 2b because of, I can call it like a deviation from the rigid rotor model. Now, can this deviation be measured? Absolutely. Now, one way to measure the deviation, right, including the deviation to right, one can write the energy expression of a diatomic molecule as E is equal to B times j plus 1 minus D times j square times j plus 1 square, where my D can be called as a distortion constant. I mean, some people also call it as a centrifugal distortion constant. I'm not going to go to the specific name. It is just called as some distortion constant. Okay, right? And what are the units? Well, my j is unitless. Okay, and I can only add species which have the same dimensions. So therefore, the D has the same units as B. And these are all positive quantities. Recall the least value of j is going to be 0. So D is also going to be a positive quantity, and therefore this explains that the gap, the gap is going to be less than 2b. It's not going to be greater than 2b. All right. So therefore, my E, including the deviation from the rigid rotor model, is given by this expression. And how do I obtain D? Well, D is something obtained empirically for the most part. What do I mean by empirically? It is obtained by looking at the spectrum and measuring that, the gap is less than 2b. So let us account for it by using a constant and a formula of this type. All right. So this is how you also get to model the purely rotational spectrum of a molecule, right? Of a diatomic molecule in particular, including the distortion constant also. Okay. Now the next idea is going to be that I'll delete this part. See, transitions of the form. Okay. Delta J is equal to plus or minus 1, right, are particularly important in microwave spectroscopy. Now, why this is, I will explain in a tutorial. Okay. In essence, it is connected with what are called as selection rules. Remember, we talked about gross selection rules. How we can compute the magnitude of the transition dipole moment, and from that some results emerge, right? So similarly, this can also be mathematically computed from that. We're not going to go there in this particular class, okay, right? So just be aware that delta J equals plus minus 1 are particularly important in microwave spectra, okay, right? Now, spectra, and when say for example delta J is equal to plus 1, right? In other words, I'm talking about a lower energy state going to a higher energy state. The series of lines is what is called as an R branch. So therefore, my R of 0 refers to R0 to R1. And similarly, my R of 1 refers to R1 to R2. In other words, from the ground rotational state to the first higher rotational energy state, and this is from the first higher rotational energy state to the second higher rotational energy state. Okay, so these are just some nomenclatures which you might encounter in various contexts of astrochemistry. Similarly, right? Similarly, your P branch. You also, when delta J equals minus 1, the rotational lines corresponding to it is what is called as your P branch. Okay, right? When delta J is minus 1, you get what is called as the P branch. Okay, so now P1, for example, okay, P1 is going to be P of 1 to P of 0, and R1, sorry, and P2 is going to be P of 2 to P of 1. All right. So that is, am I clear? So when delta J is negative 1, you get what is called as the P branch, and when delta J is positive, right, you get what is called as the P branch. But delta is defined as final minus initial. Okay, so note delta is defined as final minus initial. That's how you make sense of this delta G here. Okay, so now that we have these expressions in a pure, when you're talking about purely rotational spectrum, note in a pure rotational spectrum, right, your P1 line is the same as R0 line. All right, it makes sense, right? If you're talking about the J equals 0 to J equals 1, it's the same as you're going to be J1 to J0, right? So therefore, your I'll clarify even better. See, this is going to be J equals 0 to J equals 1, and this is J equals 1 to J equals 2, and here this is going to be J equals 1 to J equals 0, and this is J equals 2 to J equals 1. So therefore, you see that it doesn't matter whether you're like going up or coming down, the magnitude is going to be the same. Okay, but this is true only in a purely rotational spectrum. Okay, right? The moment like you talk about some vibrations also coming into the picture, there are going to be some deviations in the lines noted. Are we clear? Okay, so these are just some popular terminologies which are used in the context of microwave spectroscopy, that is purely rotational spectrum. Okay, right? And these are the series of lines that typically astronomers talk about when they say the P1 line, the R2 line, etc., when they actually detect molecules. In fact, if you recall our lecture corresponding to the detection of molecules in space, I was talking about the fact that it was from this R equal to the intensity of the R equal to 0 line and the R equal to 1 line noticed in the electronic spectra. Okay, right? Noticed in the electronic spectra that Andrew McCullough derived at the value of the temperature for the source, the molecular cloud, to be approximately around 3 Kelvin. So you may go back, right? So the R0 and R1 that I was vaguely talking about back then, they are more precisely defined, right, in this lecture. So this tells you, like how learning is actually a very non-linear process. So you have to go back and forth to actually understand the bigger picture. All right, the big and the complete picture. So these are the nomenclatures as part of the microwave spectrum. Now, the next thing we'll be looking at is, what we'll be looking into next is how we know microwave spectrum or the rotational spectroscopy. Okay, right? We shall be looking into gives us information about isotopes also. We know where exactly do you expect the lines for the isotopes to come up. Gives information isotopic species. Now, what are isotopes? Well, isotopes are species, which differ in the number of neutrons, correct? For example, you have something called as the 12 carbon monoxide and 13 carbon monoxide, where, let's assume that the oxygen, we're talking about they have the same atomic and mass numbers, right? But these differ by number of neutron, right? This has one excess neutron. These are two isotopes. Now, what microwave spectroscopy, that is like purely rotational spectrum, right? What it can teach us is that if we know the peak position of this particular species, we can identify the peak position wherein my carbon monoxide can also come. We'll do this exercise. I'll tell you how it is done. For example, let's say that the R0, given that my R0 transition, right, for 12, this isotope, the 12 carbon monoxide, is given at approximately, it happens at 115.271 gigahertz. Okay, right? Now, from this, okay, right? From this, we can find out at what position will the R0 occur for 13 carbon dioxide. We'll see how this is done. Now, what do I mean by the transition occurs at this particular frequency? It tells me that the delta E for j equal to 0 to j equal to 1. Remember, we are talking about a positive delta j that corresponds to the R line. Okay, right? Is given by 115.271 gigahertz. Okay, right? Now that we know this, right? My delta E, what is the expression for my delta E? We had obtained it, right? In terms of B and then the J's. My delta E is given by, if I'm correct, 2B times J plus 1, correct? So this is what we obtain, right? 2B times J plus 1. Now, therefore, right? Now, my the delta E, okay, right? Delta E for R0 for 12 carbon monoxide, right? Let's say, if I were to, like divide this by the value of the delta E for the same R line, the R0 line of the R0 line for 13 carbon monoxide. Okay, right? Now that is going to be given by, right? That is going to be given by what? That is going to be given by B for 12 carbon dioxide divided by the B for 13 carbon monoxide, sorry. Right? Are we good with this? In other words, right? Now this ratio, right, is given by this expression. But you understand what is your B? Your B is inversely proportional to your I. You can get the exact expression, in whatever units. No matter what the units you're going to be talking about, B is always inversely related to I. This therefore is given by the moment of inertia of my 13 carbon monoxide divided by moment of inertia of the 12 carbon monoxide. Right, I'll continue in this page. Now please recall that your moment of inertia is given by mu times r square, right? Now for the isotopes, recall that for isotopes, bond length does not change. In other words, right? In other words, what happens is that, your moments of inertia, right? I13CO by I12CO, what one can actually do is, one can actually be writing this as your, where is it? So your I13CO divided by I12CO, right? That can also be written as simply going to be the reduced mass of 13 carbon monoxide divided by the reduced mass of the 12 isotope. All right, because the R is going to be the same, right? Now this we can calculate, right? This you can calculate and find that this number is going to be approximately 7.17, and this number, that is for the 12 carbon monoxide, the reduced mass is going to be 6.85 approximately. I'll leave it to you as a homework. Find this, right? So this is what? This is roughly going to be, slightly greater than 1, right? This is going to be approximately, around 1 by 0.95 something. Okay, right? So from this, right, if you compare this expression right here, right? Now we already have been given this, that for 12 carbon monoxide, this is the frequency at which this happens, right? Now because my B, that is the rotational constant, is inversely proportional to moment of inertia, and between isotopes the bond length does not change, I have an expression for the ratios of this. And so given this number, so given this number, right, that is given this value to be, what is it, approximately around 115.2 gigahertz, right? So given this, right, you can always compute this based on this relationship right here. Are we clear? I'll leave that as a homework. Find delta, like find R naught for 13 carbon monoxide also. Straightforward, right? Having done all the steps, I'm just skipping the numericals because I wanted to teach you one more idea before this lecture ends. There are just a few minutes left. Okay, so please note that based on the position where one isotope occurs, right? The line position for one isotope, you can calculate the position for another isotope also. Now, in fact, notice that this number is not going to be much different, right? It's only going to be max 1.1 or something like that, right? This 1 divided by 0.95. So now you understand how closely, the two lines are. The line corresponding to your 12CO and 13CO, right? Now, put this in the context of the spectral line width, right? We talked about the significance of the line width in spectroscopy, right? Now, if we know the width of the line happens to be greater than the separation between these two lines, then we could never detect these molecules, right? I'm just telling you this idea to basically connect, the concepts of spectral line width, which I discussed with you in the previous lecture, with this topic right here. Please make note of this, okay? So now we understand that rotational spectroscopy can also provide information about isotopic species. Now, as the last part for today's lecture, what we shall be doing is, I shall give you a broad picture of how molecules are detected in space via, like your rotational spectroscopy. The first thing, of course, is to record the spectrum of any molecule on Earth, right? Record the rotational spectrum on Earth. The next step is obtain the spectrum from space. This is done via radio telescopy, right? And after that, see, there's already going to be a slight difference because of the Doppler shift, right? So then you have to correct for the Doppler shift. And the next step is going to be take into account, the width of a spectral line, right? Spectral width, spectral line width. Okay, I'll just put it as line width. And having done all these, I'll write it here. The next step is, after doing this, points A to D, the next step would be to check for isotopic line patterns, right? We just saw, right, between the 12 carbon and 13 carbon isotopes of carbon monoxide, right? We can clearly get, two very closely lying lines, right? So then once you check for isotopic line patterns, and once, you've checked all these points, that is points A to point E, then you can identify a molecule in space. But notice that there are going to be several sources of errors. What are all these, right? Now, you must make sure that the Doppler shift is properly accounted for, right? Now, after that, you must also make sure that, the resolution of the lines, right? That is beyond the natural line width, okay? And then, even for the isotopic patterns, you must make sure that the isotopic abundances predicted, right, are matching well. Only then you can identify. So it's actually a rather challenging area. Okay. So on that note, I shall stop today's lecture. We shall continue with some minor aspects of rotational spectroscopy, right? In fact, I want to make a very important statement. It is that microwave spectroscopy is the most important and powerful way via which molecules can be detected in space. Okay. I will substantiate the statement in the next lecture. And I'll also move on to vibrational spectroscopy as relevant to astrochemistry in the next lecture. Are we clear? So on that note, I end today's lecture. Thanks a lot.